So good evening, everyone. Today, I'm going to talk about the entire life cycle of a query execution in SparkSQL. More specifically, I'll be focusing on two aspects in this talk. So first, I'll talk about the Catalyst optimizer, which is essentially, in some ways, Spark's front-end engine. And then I'll talk about the Tungsten execution engine, which in some ways, it's Spark's back-end execution engine. So just a brief introduction about me. I am a software engineer at Databricks, where I work on SparkSQL and Spark Core. I received my PhD along with Tim at Berkeley in the AMP lab, where I personally worked on BlinkDB, which is an approximate query processing framework that was built in Spark. So let me start off this talk with a little bit of background. What exactly is going underneath the covers when you create an RDD, or a resilient distributed data set in Spark? So there are a couple of things that an RDD in Spark encodes. First, we have a set of dependencies. Given an RDD, how do we construct it? It might be coming from a text file, or it might be actually coming from a list of other RDDs via a sequence of operations. Then we have some ways of partitioning the RDD, or the data inside it. And more specifically, this also maps to how we partition the compute so that we can actually execute or operate on that RDD in a distributed fashion. And finally, we have a compute function. So the compute function is nothing but a map from each partition to an iterator of data that's actually stored within this RDD. Now, this RDD-based APIs, as you all know, is extremely powerful. In fact, everything that we have actually heard in this conference, SparkSQL, data frames, data sets, structured streaming, Spark streaming, all of these is actually built on the simple and intuitive RDD-based API. However, there are actually some things that are wrong about this API from a programmer's perspective. So one of the things, if we look at the compute function, the compute itself is actually pretty opaque to Spark. What this means is that if you are trying to write a random arbitrary function, Spark knows very little about what you are trying to do. So for example, if you're trying to do a join, or maybe a project, or a filter, all of this computation is actually opaque to Spark. And in this case, Spark cannot automatically optimize your programs in many ways that it otherwise can. Similarly, the data that's actually stored within this RDD is also opaque. And this means that Spark can actually do very little in pruning out unnecessary data if your query does not need it. So in this case, we cannot prune out unnecessary columns, or maybe like prune out unnecessary rows, even though we can, in theory, do such pruning. And finally, while this RDD API is extremely powerful, it is also pretty verbose to work with. For example, if we just look at this particular query, here we are taking something called pdata. We are trying to map something on it. Then we are calling this reduce by key operation, doing another map, and doing some kind of a collect. Right? Now, normally, it takes people like me around 10 to 15 seconds to even figure out like what's really going on. It might take some people less and more, depending on their experience with these kind of APIs. On the contrary, think about the line below. So this is the exact same query that's written in SQL. So in this case, as a lot of us can understand, it's just basically trying to select department and trying to compute an average of age, where it's grouping by each of these departments. Similarly, in the data frame or data set land, you can have a similar query that does something like pdata, group by departments, and you can then aggregate on age. Now, this should actually not come as a surprise to most of you. In fact, we all know that SQL and the structured programming model actually is much, much more efficient and concise when you want to represent high-level computations. These high-level APIs, so programs that are written in SQL, data frames, or data set, can actually describe what data operations are needed without the need of specifying how to execute these operations. And this gives us a level of conciseness, a level of beauty in describing these operations without having to worry about exact reduce by key maps and all these kind of things when we are writing code directly on RDDs. And more importantly, since now suddenly we don't have to worry about the details of implementing these operators, we can actually write much more efficient programs because your Spark or your execution engine actually knows much more about the data and the computation you're trying to do. And an optimizer, in this case, can automatically figure out the most optimal way to execute a query. So this is the high-level idea behind using structure or using SparkSQL primitives that are built on Spark. So from a high level, SparkSQL essentially can take in any user program that's written in SQL or via the data frames or the dataset API, and it represents that via a query plan. Now, a query plan in SparkSQL is essentially an abstraction of the user's program. We also call them trees. Now, Catalyst in this land essentially applies a series of transformations on each of these query plans or each of these trees and tries to basically come up with the most optimal query plan by applying a series of these transformations. And we'll talk about these trees and transformations in much more detail in the next part of the talk. Now, once we have an optimized query plan, the next step is to actually generate code that is then executed on a cluster in a distributed fashion. And that's the job of Spark's Tungsten execution engine. So all in all, we have a SQL query, or maybe something that's written via the data frame or the dataset API that gets converted into a query plan, which then basically gets converted into an optimized query plan by applying a series of transformations. And then this ultimately gets converted or generated into code that's then executed on the cluster. So let's start off by giving, let me try to explain what exactly is this abstraction of user programs or trees or query plans that I'm talking about. So let me illustrate this with a simple example. So let's say we have a query like this. In this particular case, we are joining two tables. So we have a T1 join T2. We are trying to filter on some attributes. So in this case, we are trying to make sure that the ID of the first table is equal to the ID of the second table. And the ID of the second table is actually greater than 50 multiplied by 1,000. From this, we are trying to select two attributes. One is the ID of the first table, and then we are also trying to select 1 plus 2 plus a value from the first table. And finally, we are trying to compute a sum on one of the values or one of the attributes that we selected on. So as soon as SparkSQL sees a query like this, the first step that happens within the compiler is that it tries to identify these sets of expressions in the query. Now, an expression basically represents a new value that's computed based on some input values. So in this case, sum of v is an expression because it's computed using v. Similarly, 1 plus 2 plus t1 dot value is an expression because it's computed using t1 dot value. So just intuitively, an expression is basically used to generate new columns or attributes, if you may say, from older or input attributes. Now, a query plan, on the other hand, is then used to describe the data operations, which are like aggregates, joins, filters, and those operations essentially generate a new data set based on an input data set. So here's an example where we have scans, joins, filters, project, aggregates, and each of these nodes on the right-hand side actually corresponds to operations in a SQL query. So if you look at the right, we started with a query on the left, which is just a SQL query, and we converted into a query plan. These has these sets of data operations. So you have things like aggregate, project, filters, which essentially map to what roughly the query is trying to do. And each operator is basically working on these expressions. So you have things like 1 plus 2 plus t1 dot value, which the project operator is trying to select. There might be the aggregate operator, which might be trying to produce the sum of v expression. This query plan can actually be of two types. The logical plan, which is basically what is shown in this figure, is essentially a plan that describes computation on data sets without defining how to conduct that computation. So in this particular case, the scan operator, even though it might actually be dependent on what files or what type of file format it's trying to read, the logical plan in this case would just have a single scan operator that just logically represents what the query is trying to do. Similarly, the join operator, even though it's dependent on the kind of distributions of the input data set or the size of distributions, in this case, just logically represents the kind of operations you're trying to do on this query. And we similarly have filters, projects, and aggregates. A physical plan, on the other hand, on the contrary, describes computations on data sets with specific definitions on how to do these computations. So contrary to the logical plan, we see that the scan operators in this case are converted into, let's say, a Parquet scan or JSON scan, depending on whether it was a Parquet table or a JSON table. Similarly, the exact join type in this case would now be converted into a sort merge join, depending on what the input distributions or the kind of rules that were applied by Catalyst. And this is also another example in which the aggregate operator was converted into a hash aggregate. So once we have this query plan, once we extracted these expressions and we extracted these data operators, we were able to construct this query plan. We start off with a logical query plan. And the next step Catalyst does is to apply a series of transformation on this logical query plan in order to optimize this query. Now, logically, a transformation is just a function that's basically associated with every tree, and it implements a single rule. So I'll show you what I mean by that. Let's just pick an expression that we saw before in the query. So in this specific case, this expression was trying to calculate 1 plus 2 plus t1 dot value. This expression is generally denoted by an expression tree in Spark. And the way to read this expression tree would be from bottom to top. So you see like 1 and 2 literals. They are being basically added up. And then it's being added up again with an attribute t1 dot value. So basically, any expressions that we have can be represented as an expression tree like this. Now, one of the problems with an expression tree like this is that every new value of t1 dot value would end up computing 1 plus 2 again and again. Right? So one of the very simple optimizations that we can do for just expressions like this is to just evaluate 1 plus 2 once at compile time and just make this 3 plus t1 dot value so that we don't have to do it again and again. Right? So extremely simple thing that we can do, it's called constant folding. And this is something that like almost every query processing engine does. So now how do we do this? How do we construct this expression tree on the left that we have and try to basically come up with this expression tree, 3 plus t1 dot value on the right? So in order to do this, we actually have a lot of transformations in the Catalyst code. And each of these transforms internally are defined as a partial function. Now, a partial function in Scala is essentially a function that's defined for a subset of its possible arguments. So as an example, let's say that we had an expression like this. A partial function would essentially match the case class like this, and it will try to see if an expression tree actually matches something on this lines. So in this case, it's trying to match something along the lines of add. In case it has 2 literals of string type, and in case it does, it will try to convert it into a literal of x plus y. Again, the intuition here is we would like to match something along the lines of add of 1 plus 2 and try to convert it into literal of 3. So in order to basically, when this expression or when this transformation actually gets applied to this tree, what happens is that you start off with the root node. In this specific case, we find out that the first node has a left child, which is also an add. So this expression or this function would not really apply to this. But the second child actually has 2 literals, which are both integer types, in which case we would basically map and then convert this expression tree into a new literal of 3. So again, this is a very simple illustrative example. But from a higher level, when you think of Catalyst, think of it as just a sequence of transformations. Think of it as a corpus of transformations that are written by people like you and me. And there are hundreds and hundreds of transformations in the Catalyst code that try to basically optimize your query by looking at these query plans, these expression trees, and try to make intelligent decisions based on this data while guaranteeing correctness. So here are some different examples of what we can do when we can actually have these transformations on the query plan. So in this particular case, let's go back to the old query that we had. We had the scan operators, T1 and T2. They were being joined, filtered, projected, and aggregated. Now, one of the cool things that we can do in queries like this is called predicate pushdown. Again, a standard database optimization that basically pushes down the filters as close to the data source as possible. And the intuition here is pretty obvious. We would like to actually prune the data that's not necessary as soon as possible so that your query does not have to process it. In this specific case, the predicate pushdown rule would basically match this particular join or filter operator, and it will then rewrite the query plan based on the case class or the partial function that I just mentioned before. So in this case, we would basically identify that the 2 predicates in this filter, t1.id equal to t2.id, this can be pushed inside the join. And the other predicate, t2.id greater than 50 multiplied by 1,000, can actually be pushed right down to the data source. which is the table T2. Similarly, we can also do smarter things around constant folding that I just mentioned before. So things like 1 plus 2 plus T1 dot value can be automatically rewritten to 3 plus T1 dot value at compile time, and things like 50 dot 1000 can just be rewritten to 50,000. So again, very simple rules, but we can apply them continuously in order to optimize your query. Another possible rule is called column pruning. So normally, your data sets can actually have a large number of columns, but as we saw in this query, we only needed 3 columns to compute the output. We needed T1.id, we needed T2.id, and then we also needed T1.value. So in this particular case, the column pruning rule will be able to automatically insert these project operators that only project or only select these particular columns from the underlying data, because your query just needs those to compute the final answer. So all in all, we have like these sequence of transformation. As I mentioned, the Catalyst code actually contains a lot of these transformations that can then be applied based on some rules, based on some heuristics. There might be some cost models involved. But all in all, the high-level idea here is that we take an unoptimized query plan, and we try to apply these series of transformations, these series of partial functions, to come up with the most optimized query plan to execute your query. And that's the key idea behind the Catalyst optimizer and the execution engine. So just to recap, we talked about 2 things in Catalyst. We talked about the query plan, in which case we talked about expressions, how you can extract expressions from your query. And then we also talk about these data operators that can be used to build a query plan. And then we talked about these series of transformations that can be applied as partial functions to your query plan in order to generate an optimized query plan, which can then be executed on a cluster. So let me now just give a brief overview of how do you execute this query plan on the actual cluster. So this is essentially the job of our Tungsten execution engine, which generates code based on which generates some kind of an optimized code based on the query plan that Catalyst generated, and then it tries to execute it on the cluster. So in order to describe how this code generation works, let's take an example of yet another query. So in this particular case, it's a simpler query than before. It's just trying to select some count star from a table store sales, and it's trying to filter on some attribute, in this case, SS item SK equal to 1000. Now, the Catalyst generated query plan would look something like this in this case. You have a scan operator at the bottom. You might be then filtering this particular attribute SS item SK equal to 1000. The project operator in this case would just prune out all the columns because your query does not need it. And then finally, the aggregate operator would compute the count. Now, the way many traditional databases, including Spark 1.6 and before, executed this query was using this Volcano iterator model. Now, this Volcano iterator model has pretty much been the state of art in the database community for almost 30 years, and almost all query processing engines and standard databases, until very recently, actually use this to execute the query. Now, the key idea behind executing a query or generating code using the Volcano iterator model is that for each operator that we saw in the query plan, so in this case, we had 4 operators in the query plan. For each of these operators, we basically have to implement an iterator interface that takes in record from the operator below it, tries to do some processing, and then it basically outputs that record optionally to the operator above it. So if we look at the filter operator here, it will try to read some record from the scan operator, and then it will optionally output some records to the project operator. And each of these operators need to implement the same interface. So going back to the code, this is just an example of the code for the filter operator. And again, it implements an iterator interface. So you see a def next there that returns an row optionally. And like essentially, it would basically evaluate a certain predicate. And then it is also pulling the particular row from its child. So you see like the child.next call tries to evaluate the predicate and then optionally returns the row to the upstream operator. So now this Volcano iterator model has a couple of advantages. This type of code is actually easy to write. Whenever you introduce a new operator in Spark, you don't have to worry about how it interacts with all the other operators. And second, this type of code is really composable. So when I write or when you actually see the code for a filter operator, you don't really have to worry about what operator is basically before it or what operator is after it. So there can be a scan operator before the filter operator or a project operator before the filter operator. All in all, this type of programming model or the volcano iterator model doesn't really care about these semantics, and just things are very composable and they hook pretty neatly. That said, there are actually a number of downsides of this volcano iterator model. First of all, there are just too many virtual function calls. Since you're agnostic to the operator that's below you, you really have no idea where the input data or the row is coming from. So it's all dynamic dispatching at runtime. Second, each operator now has to write the intermediate row that it's trying to send to the upstream operator into memory, or it could be even L1, L2, L3 cache. But the point I'm trying to make here is that this actually makes memory writes or reads the bottleneck now. So imagine reading and writing billions of rows to memory in which each of these upstream operators now has to read it. Your memory quickly becomes a new bottleneck. And finally, this type of code that we saw in the volcano iterator model was very confusing for the compiler. So you cannot really take advantage of many modern CPU features, such as SIMD, pipelining, prefetching, branch prediction, many of the things that like modern chips are designed to optimize for. So in order to get around this problem, we started this effort around whole state code generation in 2.0, and this is continuing in subsequent releases of Spark. And the whole idea behind this is to actually make Spark act as a compiler. And what I mean by that is, here is a query plan that was generated by Catalyst. In this case, instead of actually fusing in code via the volcano iterator model or via the iterator model for each of these operators, Spark would essentially try to generate code that looks like something on the right. So in this particular case, the scan operator would roughly map to the for loop. The filter operator in this case would just map to a filter condition or an if condition. There is no project code because there are no columns to deal with. The aggregate, on the other hand, would just basically map to some code that is incrementing these counts. So all in all, the idea behind whole state code generation is that we can actually fuse these operators together so that we would try to actually generate code in Spark that looks almost like hand-optimized code. So this code that we just saw is something that looks like hand-optimized code, something that I and you would write when we are trying to basically do a filter and a count on a particular data set. And the idea behind this is that we can identify chains of these operators or stages and then compile each stage into a single function. And the goal here is to actually achieve the functionality of a general-purpose execution engine. We would ideally want to generate the code for any plan that Catalyst produces in Spark, but we want the performance as if we really hand-build the system, and we are actually hand-writing the code for each query plan that Catalyst is generating. Now, I'll not actually go into too many details about how we exactly generate the code and how each operator actually maps to the generated code. But I'll give you a reference on this excellent paper by Thomas Newman in VLDB 2011. And this is essentially the whole theory behind what we have implemented in Spark. So this paper actually talks about how each operator can then be fused together, what operators cannot be fused together, what are these compilation boundaries and things like that. And what we have done is we have basically implemented a lot of approaches from this paper into doing whole state code generation in Spark. So I just have a couple of more slides around performance. And this is just to give an idea about how much performance benefits whole state code generation actually got us in SparkSQL. So essentially, these are some of the operator benchmarks that I have. These are very familiar operators in Spark, which is the filter operator, aggregates, hash joins, and things like that. And the things that it compares is this cost of processing per row in SparkSQL. And the cost is in nanoseconds. And it compares Spark 1.6, which did not have whole state code generation, to Spark 2.0, which did have whole state code generation. So as we see that for many of these filter aggregates, hash joins, we see around 50 to 30 times speedups in many of these cases. For things like sort, we see around 10 to 100 times speedups. The speedups are not so much noticeable in things like sort merge join because shuffling in this case is still the bottleneck. And finally, this is something I didn't really talk about in this particular talk, but we also have a vectorized Parquet reader in Spark, which essentially gives us around 10 times speedup or an order of magnitude speedup if you're trying to just read Parquet data inside of Spark. This is a similar slide around performance, but it talks about an end-to-end query execution. So this is the TPCDS benchmark, which we executed on a scale factor of 1500 on 100 cores. The y-axis here is the query response time, and the x-axis here is the list of queries that could be executed in Spark 1.6. So I believe there are 49 of them, whereas Spark 2.0 can actually execute all 99 of the TPCDS queries. But for a fair comparison, we see that 2.0 is on an average around 2 to 3 times faster than 1.6. So again, the lower the bar, it's better because the y-axis is the query response time. So finally, I'm going to talk about 3 things that I'm really excited about when we talk about like the performance of the Spark's execution engine. So in Spark 2.0, one of the biggest things that's going to come in is the cost-based optimizer. And this is primarily an effort that was led by Huawei. And the idea here is to actually leverage column and table level statistics to optimize joins and aggregates. And as part of this, we have worked on a statistics collection framework in Spark 2.0. And there are active efforts in basically integrating a cost-based optimizer for Spark 2.0. And in order to think about a cost-based optimizer, think exactly in terms of these transformations or these conversions between the query plans. But now with this cost-based optimizers, we would basically have a better idea about the cardinalities, about the distribution of the data. And in this case, these transformations can actually make better decisions. So for example, we can probably better decide the order of doing the joins, or whether we would like to broadcast one side of the join or the other. The other big effort that's basically going around is in boosting Spark's performance on many core machines. And in this specific case, we have efforts in the direction of having in-memory single-node shuffle. And then finally, we are constantly working in improving the quality of generated code, and then having better integration with in-memory column format in Spark. So that's all I had prepared, and I'll be very happy to take any questions. Thank you.
Thanks a lot, Samir. So we have the time for a few questions, and we have 2 microphones here. Feel free to use it.
Hi. I was wondering if you could comment on how this compares to Hive's Calcite or other CBOs.
So I don't really have the numbers, but the basic idea behind optimizing query plans and essentially doing these transformations is very, very similar. Regarding cost-based optimizers, we are actually leveraging a lot of past research that is done in the database community around like IBM DB2, which really pioneered a lot of work around like cardinality estimation and statistics generation. There are a lot of work around like, the SQL Server done by Microsoft. So we are actually leveraging a lot of ideas that are done like on the research level in the database community. So we hope to actually get like a lot of benefits that have been done as well. So it's kind of like basically leveraging a lot of like effort done already in the database community and trying to basically bring those ideas to Catalyst and to Spark.
Okay, so we have a question on the right.
Can you go into a little more detail about the in-memory single-node shuffle?
That's a great question, and I got the same question in the morning as well. So actually, I would like to point you to a talk that was given by Shifan Pu at Spark Summit Europe last year. And this talk is actually talking, this talk gives a great overview of this entire effort that's being done in the in-memory shuffle. So I would actually recommend like looking at the talk. It talks about like a lot of trade-offs, what exactly we are trying to do. And then, there are a lot of like open patches around like in-memory shuffle in Spark that you can look at.
Yes, you mentioned that Tungsten uses in-memory columnar format, and then I looked at it, or I went to a presentation today about Apache Arrow. So I was wondering, is there work already being done to let Tungsten use Apache Arrow, or is that just kind of a long way roadmap thing?
Right, that's a great question. So essentially, the in-memory column format in Spark essentially does not use Apache Arrow right now. What we did was we basically did something that actually natively, we built something inside of Spark. The idea is pretty similar. Basically, this in-memory column format allows you to have zero copy data load from Parquet. So the idea behind Apache Arrow and all these things is very, very similar. It's just a matter of time. Maybe we would basically be using Apache Arrow if Apache Arrow is able to basically integrate it with all these column format. But right now, our in-memory column format is actually something that's built inside of Spark. So we do not directly use Apache Arrow in that case.
question on my right.
So I'm wondering about if you have the same data in multiple formats, does Spark today have some kind of way of make a decision on which of the access methods it will use? Or is that something, is it in the works?
Which of the what?
So suppose that you have like a Parquet file and you have a whatever other format you use.
JSON file.
Is Spark aware of the fact that, say, these two are the same one and he could choose which one, whichever is better?
I see. No, currently not. So currently, I think like Spark will not be able to, if your question is, can Spark actually identify somehow that this actually points to the same data?
Well, if it knew that it's the same data, would it be able to use that?
So what do you mean by use here? Like, is it just like
so for example, in databases, if you have a tree index on something, and you have the same thing in you could choose to access it sequentially, or you could choose to access it through the indexing. And you could have, I'm just wondering, I'm not too familiar with what Spark does in this case, but I'm just wondering what the state of the optimization is.
Right. So like Spark does not really right now have any transformation to actually like choose your data source based on the query. But again, I mean, if this is something that's general enough, like it's just a matter of basically adding such a transformation in Catalyst. So depending on the query plan, you can basically add a transformation function like this.
Question on my left.
So my question is regarding retaining the execution plan. Like in traditional databases, right? If you have a stored procedures which is compiled, and the execution plan is retained so that next time it can leverage it, it doesn't have to build it. In this case, is it like you are rebuilding the plan every time it hits the query, right?
Yeah, great question. So yeah, I mean, basically we could do some things like that. Like if you're executing the same query again, or like even, I mean, there is like a lot of work done in the past, like database community around like reusing subtrees of the, so you already know the best way to optimize like a subtree. And if you see that subtree again, you can actually plug that subtree, the optimized subtree in that query. Unfortunately, Spark does not like do things like that right now.
Okay.
But again, in future, I think we would be able to leverage a lot of work around that area.
Thank you.
So two more questions, and then we'll finish the session.
Okay. Thank you. Very, very good talk. So my question is about the number of partitions when there is a join involved in the query, which is one of the key tunes that we have to usually do in order to improve the efficiency. It is the case that still in SparkSQL, we have to manually do that, right? Because that adaptive shuffling hasn't been released yet. So could you please elaborate a little bit more in that? Because it seems to me that that's key to embracing SparkSQL as a production for big data pipelines.
So is the question like when will like adaptive shuffling be available in SparkSQL?
When or what else is being doing, if anything, or yeah, anything that you can.
Right. So I think in general, like I mean, once we have this kind of like more fine-grained cardinality estimation. So again, like I mean, coming back to the CBO efforts, if I know exactly what is the cardinality in like I mean, basically in each of your partitions, we can actually do this adaptive shuffling and basically auto-optimize your query. Right. So I think like once we have those things in, maybe in subsequent releases of Spark, like 2.3 and 2.4, we would be actually able to do things that you just talked about. Right now, like it's more of a hand-optimized thing in which like you need to really figure out like how your query is distributed, and then you do basically what you just described.
Okay, thank you very much.
And our last question.
So my question is kind of more specific to a specific problem. So yeah, data frame is good, and SparkSQL is good for the tabular data and well-defined schema, which land well. But in the real world, the data could be JSON and nested, and also some of the attributes could take different structure. For example, address could be a string, or could be a structure with the postcode, zip code, kind of street, state, something like that. So if we, basically if we encounter this kind of dilemma, so we cannot align the schema, so we have to give up using data frame or SQL just because we cannot flatten it, because the area of objects cannot be flattened at all.
Makes sense.
So in yours kind of vision, is there kind of some direction Spark community could go kind of use this kind of plan to?
Makes sense. So I actually touched on this problem. I mean, this is a very valid problem, and this is like one of the biggest problem when you do like things like ETL with Spark. And I touched like some of these things like in my talk in the morning. But essentially, like there are two things we can do here. One is like when you try to read JSON and CSV data, Spark actually supports different parse modes when you try to read this data. So I mean, this parse modes might be like permissive. You might have like a fail fast mode or a drop malform mode, depending on whether you would just want to drop all the bad columns, or maybe you want to like look at the bad columns and things like that. So one thing is when you try to create a data frame, you can actually give this option of like parsing the input record based on like essentially like these parse modes. That said, once you actually have identified these bad records and you try to basically flatten the arrays or like maps and things like that, that would actually require some manipulation of the underlying data. So one of the things that actually is going to come in Spark 2.3 or like even like subsequent releases is this thing called support for higher order functions. And the key idea behind this is that you can then be able to write functions like transform, reduce, maps, and things like that directly on like your SQL query. So imagine a deeply nested table which has like many columns and like a really nested structure with arrays and things like that. You should then be able to write something like a map which takes in any of these fields, and then you can actually write a function that can either flatten or like basically work with that field. So that's something that we are kind of like working on. And the ETA is around like, I mean, 2.3 and 2.4. But until then, like there are a lot of like parser modes that we can leverage to basically just like prune out or even look at this data so that we can actually like deal with this better. Did I answer your question?
Oh, yeah, that's great. Nice to hear. Thank you.
All right, let's thank Samir again. Thanks again for the great talk.